Everybody, so I had already made the video and realized I forgot to turn the camera on, so I'm redoing the Euler's method section. So I apologize for that, but I wanted to make sure you all got a chance to see this. So we're going to do what's called Euler's method. It is not Euler. It's not like Bueller's day off. This is pronounced Euler's method. Okay. Euler was also known. He was the one who discovered E, which is 2.71828, and so on. What Euler's method is, it's a numerical approximation for to the solution of a differential equation. Okay, we're computing points on a solution curve. Remember, in some cases, we can't find the equation for the curve, but we can always find a graphical solution on using slope fields. Euler's method is simply an iterative numerical method of writing a tangent line, evaluating the tangent line for a new point, and then writing another tangent line, evaluating the tangent line for another new point. So the idea is this. Okay, we're given, if you look at one, we're given a slope, we're given the slope at any point, we're given a point. Okay, and then we're also given a change in x. So what we're going to do is we're going to start at our given point, which is 1, -2. All right, we're going to then do a slope at that point. So we're going to draw a tangent line. Okay, and we're going to go over some distance, which we're going to call delta x. Okay, and then we go over that amount and we plug in, or we substitute into our tangent line, and we find a new y. So we get this point. Okay, and then we're going to come to this point and write another tangent line, and we're going to go over so much, find a new point. Okay, and then we're going to write another tangent line. Okay, so if you really think about it, we're coming up with an approximation for our curve. Okay, by doing a series of tangent lines. Okay, all right. So I'm going to go ahead and do our first example, and we're going to do 2 of these. Typically, you'll do 2 iterations. You might at some point do 3. Okay, all right. So we have to be given a differential equation because that's our slope at any point, an initial point, and how much we're moving to the right each time. So we're going to do 2 iterations, which will give us an approximation not at 3, it's actually at x is 2. Why? Because when I start with 1 and I go over a half twice, I start at 1, I'm adding 1, I get a final location of 2. If we do 4 iterations, if I did 0.5 times 4 here, then I'd actually get to 3, but we're only going to do 2. All right, so we're going to find y of 2, and 2 iterations mean we will write 2 tangent lines, 1 at the first point, then 1 at the second to approximate the final. Okay, so if you look at this, our slope at any point is dy dx, is our slope at any point is 2x, okay? And our initial point is 1, -2. All right, so we're going to write our tangent line based on that. So if we look at x is 1, at x is 1, our slope is 2 times 1, which is 2. Okay, so we have a point and a slope, so let's write that tangent line. And we're good with this. We get what? Y plus 2 is equal to our slope, which is 2, times x minus 1. All right, so now we're going to jump over half a unit to the right from 1. So what does that mean it's going to be? Is my new x is going to be our initial plus our change, which is 0.5. So we're at 1.5. So we're now going to approximate our curve at our new value, like we said we would here, to find our new y value. We know our new x is at 1.5. We got to find our new y. So I'm going to substitute it in here, and I would get, well, if I bring the 2 over, I get -2 plus 2 times 1.5 minus 1. But miraculously, this is our delta x, right? And whenever you plug in that new value and you subtract where you were, it becomes our delta x. So this is negative 2 plus 2 times a half, or 0.5. So it's negative 2 plus 1, and we're at negative 1. So it's our y value of negative 1. So what is our new point? Well, our x was at 1.5, and our y was at negative 1. Okay? All right, so now we're going to still write our tangent lines. We got to find our new slope. Okay, and I'm still using this. It's computing our new slope. Well, that's now 2 times 1.5. So my slope is 3. Okay? So if we go ahead and now do our tangent line based on our slope of 3 and our new point, that's going to be y plus 1 is equal to 3 times x minus 1.5. Okay? So I'm going to go a half a unit over, or I could go plug in, well, if we were at 1.5 and we go a half to the right, okay, we're going to go plug in 2, or this just becomes 0.5. So if I go compute my new value, I move this over and I get negative 1 plus 3 times 0.5. Well, that's negative 1 plus, what is that? 1.5. Half of 3 is 1.5. We end up at 0.5. So what is our final point? Is y of 2, because that was our approximation, is equal to 0.5. Okay? Well, I want to show you what we're actually approximating. What is our function? Well, if we start with dy dx is equal to 2x, and I separate our variables, I'm going to get dy is equal to 2x dx. Okay, if I integrate that, I get y on the left. On the other side, I get x squared plus a constant. Okay, well, now I'm going to use my initial point as a condition. So that's going to be y is negative 2, x is 1, squared is still 1, plus c. So c is negative 3. So what is our function? It's y is equal to x squared minus 3. So now if I were to go plug in 2, which is what we were actually approximating here, plug in 2 for x, I would get 2 squared minus 3, so y is 1. We came up with a half, so we're reasonably close. Well, so it begs the question, how can we make it better? Well, we need we need our delta x to be smaller, right? Because the closer our points are, the more accurate it's going to be, right? All right. So that was our first one. We did 2 iterations on this one. All right. So this one is a little bit is numerically a little bit more complex here. Okay, so we're starting at x at the point 1, 2. Okay, but now we're going to approximate 1.2 at the end, jumping over 0.1 now. So our delta x is 0.1. All right, so we need to go find our slope. Okay, and our slope this time, remember, we're using the 0.12 in our new differential equation. So x is 1 on the top. On the bottom, I get 2 times 1 plus 2, which is 1/4. So my slope is 1/4. So if we write our tangent line, it's y minus 2 is equal to 1/4 times x minus 1. All right, and if we jump over 1 or 0.1 units from 1, that's when x is equal to 1.1, or, yeah, it becomes 0.1 here. So I would get y is equal to 2 plus a fourth times 0.1. Well, remember, this is really 0.25 times 0.1, which adds another 0, so that's really 2 plus 0.025, or 2.025. And you could certainly have done that with a calculator, and that's fine. Because the second part, the second iteration, we're going to have to use it. So our new point is at 1.1, comma 2.025. Okay? All right, and I'm going to bring my calculator up here. I'll just bring my Desmos up. I'm going to clear it all off. Okay. So we have our point. Now we got to go compute our new slope. And this one gets messy. Okay, so my slope up top is going to be 1.1. On the bottom is going to be 2.1, 2 times 1.1, or 2.2, plus our 2.025. So if we go type that, I'm going to do 1.1 divided by parentheses 2.2 plus 2.025. My slope is 0.260. 4. I'll go one more decimal for giggles. All right, so let's go write that tangent line. It's y minus 2.025 is equal to 0.2604 times x minus 1.1. All right, now we're going to plug in 1.2 because that's our jump over, or in other words, this is just going to become 0.1. So we get what y is equal to 2.025 plus 0.2604 times 0.1. That moves the decimal over. So this becomes 0.0260, and I'm going to leave it right there. And yes, you could use a calculator, but if I add those together, I believe we get 2.0... 5.1. Okay, if you don't believe me, okay, 2.025 plus 0.026 is 2.051. So what is our approximation at 1.2? Is 2.051. Okay, so our final values is at 1.2, our y value is 2.051. Okay, so that's Euler's method. It's an iterative process. Okay, I came back and did this one on the part 3 video, and I did this antiderivative on the part 3 video. So do take a look at those. Just so you know, the most in terms of iterations you'll have to do is 3. I've only done ones with 2 iterations. Okay. The other thing is sometimes some books do and some explanations do this as a table. And I had done it as a table originally, but I want to tell you what happened was after a couple of months when we had to come back and do an Euler's method question, people couldn't remember what the table labels were and how it worked. So I kind of went to the double tangent line or writing 3 tangent lines if you have to do three iterations, just because it was a lot less to remember. And doing tangent lines is easy. So, all right, everybody, thank you. Have a good rest of your day. Okay, bye.